Good day, viewers. I am creating these videos to support teachers of maths in helping their learners make sense of mathematical concepts and their associated procedures and processes. And today I thought I'd take a look at expanding quadratic expressions. So what I've got here is I've got my algebra tiles, and although you won't have necessarily these labeled if you've got the physical manipulative, I'm going to turn the labels on for this. Of course, it doesn't have to be X. I can change the label to whatever I like, so I can change it to Y or P or K or N if I want to, but for now I'm going to keep it with X. Okay, and the idea is we're going to look at what does it mean to expand a quadratic. Well, of course, there are a couple of different ways we can get quadratic expressions from expansion, and probably one of the most basic is to look at something like x times 2x plus 5. So what do I want my learners to understand from this? Well, the way I want to model this is to say, well, what I'd like you to do is to build me a rectangle with no gaps and no overlaps that has a width of, in this case, x, and a length of 2x plus 5. And if learners are familiar with this from perhaps an area model of multiplication or using a similar thing in expanding linear expressions, and I do have a video on expanding linear expressions, which you may want to watch first before looking at this because it explains a lot of stuff we might use in here, then this should pose no problem. It should be sort of familiar to learners, hopefully, by this point. And so we can start tiling this space and filling this area to create a rectangle with no gaps and no overlaps. And, you know, as sort of with linear expressions, if you've watched that video, what you might get is people wanting to sort of put x's in here first of all, and they'll quickly realize they can't do that because although this length is x, these lengths are 1, and 1 doesn't match up nicely to x. And it's always worth making sure, if you're working with the physical manipulative, that your value of x is not an integer multiple of the length of 1, because if it is, then you may run into problems with things like that. So instead, I'm going to put an x squared in here. Okay, so I've got an x squared because that's an x by x square in effect. So I've got a single x squared that I can put in there. And similarly, I can put a single x squared in there. And then what about in here? Well, in here, of course, I can put 5 of my x's because each of these is a little 1 by x rectangle. And if I want to partially abstract that, I might draw a picture of what it is I'm creating. So I'm creating a rectangle which has a width of x and a length of 2x plus 5. But of course, that rectangle has actually been into 2 parts, which is why I've split it into 2 parts, because it's come in 2 parts. There's this part, which is the x by 2x, and to tile that, I've used 2x squared. And then to tile this bit, because it's 5 by x, I've used 5x's. And so we can see the expansion to that is just 2x squared plus 5x's. And of course, that's what happens when I calculate the area of a rectangle. If I calculate the area of a rectangle in 2 parts, once I finish calculating their separate areas, I add their 2 parts together. But this expression won't simplify. And again, I have put a video together about simplifying linear or simplifying expressions in general by collecting like terms, if you want to watch that first. What happens then if I change this so that instead of positive it is negative? Well, again, it's very similar to what I showed in the expanding linear expressions. Let's say I want to change it into x, 2x minus 5. Well, then changing this to a -5 means I'm going to flip these tiles around. So now it's a -5. And some people get a bit sort of iffy about negative length or negative area here, but it is possible to model these things. The idea being now this is a -1 times x area, and so that would be -x. And as I said in the linear expressions one, the act of flipping any part of the heading of a column or row is to flip anything in that column. So the fact that I flipped this -1 means I'm going to have flipped this whole column. There's only one thing in that column, of course, it's the -x. And so there we can see the 2x minus 5 expansion being 2x squared minus 5x. And then I could even do the same thing here, and I could say, what about if that was negative as well? Well, of course, now that I'm flipping this, that means everything in this row is going to flip, which means because there's only the one row, everything is going to flip. So those x squareds are going to flip. And now because this is -1 times -x, this is flipping back to a positive again. And so I can see my results being -2x squared plus 5x or 5x minus 2x squared, depending on how you want to write that expression. What about then if I am expanding two linear binomials? So something like x plus 3 by 2x plus 5. Well, the beauty of this, of course, is that it is no different. The model here is no different. I am still saying to my learners, can you create for me a rectangle with no gaps and no overlaps that has that length and width? So it has a width, say, of x plus 3. And of course, it doesn't matter which one is length and which one is width here. And that's part of, getting to grips with this sort of thing, is recognizing that it's the same rectangle, produced just a rotation of it, but it's the same total area value no matter which way around they go. And so what I can see here now, of course, is that I'm going to have my 2x squared in there, and I'm going to have my 5x's in here, just like I had in my first expansion, because the part of this, the top half of this, a half in inverted commas there, because it's not really a half of it, of course, but the top part of this is the same as the first thing I looked at, x by 2x plus 5. But now I've also got my 3x's there, and in fact another 3x's there, and then a 3 by 5 rectangle in the bottom corner, which I'll use 15 tiles. And again, I can draw a sort of partial abstraction of that and say, well, I built a rectangle. It's not a very good rectangle, but I did build a rectangle which has a width of x plus 3 and a length of 2x plus 5. But we can see now that that's actually been built in 4 parts. I have a blue part, an x squared part up here where I've used 2x squared. I've got a part over here where I've used some vertical x's. I've used 5 vertical x's. I have a green part down here where I've used horizontal x's, and so I have used 6 horizontal x's there. And then I've got a yellow part down here where I've used 15 ones. Okay, and again, what's really useful, particularly if you're going to go on to explore factorization in the same sort of way, is learners recognizing that even without the colors, because sometimes these things may be red, even without the colors, we are building this expression in 4 parts. We have a squared part, which it comes between where the length and width of the rectangle have a variable length. And then we have some vertical x's where our ones are getting multiplied by our variable. We have some horizontal rods where our ones down the width are being multiplied by our variable across the length, and then we have some pure numerical part where we have number multiplied by number. And again, what we would normally do here, of course, is add these 4 bits together. Whenever we calculate the area of a large shape by breaking into parts, the final thing we do is sum the separate areas that we have. So I've got 2x squared, and then I've got 5x and 6x, so I've used 11x's all together, and then 15. And again, I can do things with this in terms of making things negative or positive. So I could make the 3 negative, but keep the 5 positive. And because I make the 3 negative, so I'm going to flip the 3, the effect that that is going to have is to flip everything in those 3 rows. So I'm going to flip all of these. I'm going to cheat and just copy over. And then similarly, I'm going to flip all of these. And so we can see now that rather than these 6x being positive, because this was minus 3x rather than plus 3x, the 6x now is negative, the 15 is now negative. This, you might even write it as plus negative 3. That becomes negative, that becomes negative, and that affects the eventual area that I have. And if I choose to, I can even sort of start zero pairing some of these things up to show that a lot of this will disappear when it comes to the simplifying. But in terms of the value of the area, the 5x minus the 6x leaves me a value of negative 1x. And that's where that goes. And then similarly, I could flip these around, and if I flip these around, then I would get obviously all of these 5x's negative, but then these would go back positive because the negative ones and the negative ones, they would go back positive. Or I could even make it, negative 2x here, so I could flip my 2x, and that will flip everything in these 2 columns. So it will flip the squares, so the squares will become negative, but it will also flip the x's. So because I've cheated and copied down, I'm now causing myself problems for that. There we are. See, they're all zero pairing away when I click on them now, but that's fine. There they are, flipped back. And we can see now that, with x plus 3 and negative 2x plus 5, sorry, x minus 3 plus negative 2x plus 5, I have that flipped. And then I have those flipped, but because these are flipped twice, they stay positive. So I have 11x minus 2x squared and minus 15, or negative 2x squared plus 11x minus 15, or however you want to sort of write that expression in ascending, descending, or mixed powers of x. So that is just a shortish video on making sense of what's happening when we're expanding quadratic expressions using algebra tiles, and support making sense of what's happening using algebra tiles. As always, I'd like to say a big thank you to mathspot.com and its creator, Jonathan Hall, who has provided a wonderful website which not only houses all these virtual manipulatives that I'm using to create these videos, but also houses a wealth of other material for teachers of maths. And really, if you've not been on that yet, if this is the first video of mine that you've watched and you've not seen me sort of raving about this website on any of my other videos, or if you have and you still haven't gotten around to going to look at it, then please do go and look at it, because it will make your job as a maths teacher easier once you see the amount of stuff that Jonathan's put together on that site. And also, of course, if you are interested in manipulatives and visuals and using them to support making sense of maths concepts and their associated procedures and practices, processes, then you can visit my website, visiblemaths.co.uk, and amongst the different things that you will find there, you will find a link to the publisher of my book, Visible Maths. The publisher is Crown House, and on their website you can see some sample pages, and you can, if it takes your fancy, place an order. I'll be making these videos throughout lockdown and potentially beyond. So if you have a particular concept or procedure or process that you think you'd like to see, how does that work with manipulatives, then please do get in touch and I will endeavour to create one for you. Thank you very much for your kind attention.